Although our project is about battery management and control systems on electric vehicles, our group ID is BO51141, and our members contains 电机三甲吕家佑 and 部分三乙周佑哲 and 电机三乙李天福. So in the first part, I'm going to introduce our project. With the rapid proliferation of electric vehicles and energy storage systems, the performance of battery management systems has become increasingly critical to the overall system lifespan and efficiency. This project aims to design a cloud-based, intelligent, and low-power BMS that incorporates deep learning techniques for battery state prediction, and to implement it on a simulated electric vehicle platform. So the system uploads battery module data to the cloud in real time and provides web-based monitoring, anomaly alerts, and data visualization through front-end and back-end integration. On the hardware side, a bidirectional flyback power converter is used to achieve active energy balancing, paired with an STM32 controller to enable efficient power scheduling. Part 2, I'm going to introduce our research methodology. So first, we integrate battery modules, microcontrollers, bidirectional flyback converters, and sensors to build an intelligent battery management platform. Second, we use deep learning to predict SOC, SOH temperature. After model compression, deploy the model on the STM32 controller. And third, we utilize the Vite with ReactJAX fast API architectures, establish bidirectional communication between local and cloud systems via UART, Modbus, and store data and anomaly logs using MongoDB. Fourth, we design a cross-platform web interface to monitor individual cells, modules, and overall status in real time, providing anomaly alerts and chain analysis. Fifth, we integrate the system into an electric scooter simulation platform and conduct testing and adjustments for various scenarios such as steady riding, rapid acceleration, and traffic congestion. In part 3, I'm going to introduce our progress report. The cloud system of completed tasks. A virtual private server has been secured. I use Oracle Cloud as VPS provider, and the website server, API server, and database have been successfully deployed. Template web page has also been uploaded to a server, although the database is not yet fully connected to live data. The website's usability can already be tested. The web page is accessible via the server's IP address, and requests can be sent to the API server to retrieve data from the database.
Hi, I'm B11130228. My name is Zhou Youzhe, and I'm going to talk about the rest of the completed tasks that we made. So the first one is we did the research on hardware, on the circuits topology, and this picture is the simulates circuits on MATLAB. And for the output, this is the simulation's output. The red part is the supercapacitor's output current, and the blue one is the load current. So the red one should support the main battery's output current so that it helps to reduce the inrush current during the rush output. And this is the design for our supercapacitor module and gate driver and converter. We finished the design of the schematic and the layout. For the AI system, we successfully developed a LSTM-based AI model. On the left-hand side is the structure. We have CNN model and a CNN and RNN combined. And on the right-hand side, we use the knowledge distillation technique to compress the size of the model, which over 99%, and only increase about 1.5% of error rate. And we also do the BMS circuits simulation. This is the active balancing circuits topology, which is bidirectional flyback. On the left-hand side, we do the simplest simulate, and on the right-hand side is the outputs of this circuits, which is optimal. And this is the challenges that we encountered for the hybrid control system. We face that the compatibility with Windows 11 and firmware is not matched, so we have to modify a lot of code and syntax. And for the cloud system, we spend a lot of time setting up the reverse proxy server and configuring external port access. This process was quite complicated by the unintuitive design of the hosting provider's configuration interface. So we do a lot of research on it. And for the AI model, since the STM32 platform doesn't support a lot of things, which is PyTorch LSTM architecture, so we move the PyTorch to TensorFlow so that we can use their STM architecture. And STM32 lacks support for various quantization methods, so we have to choose another way to achieve the goal. For the cloud system, we do a lot of research, read a lot of articles, and in the end, we successfully configured a server to allow users to connect from external networks and for the AI system, so that we know the STM32 doesn't support a lot of quantization methods, such as supervised quantization methods and Q-Keras. So we explore another way, which is knowledge distillation. We successfully achieved significant model size reduction with effective performance retention. Thank you.
Now I am going to explain our Gantt chart. In this bound, our main goals are back-end server and database construction and BMS hardware design. Next, I will introduce our work assignment. Tianfu is responsible for control system. Youzhe is responsible for battery management system. And Jiayou is responsible for cloud system. After that, let's look at the backend estimation. The total cost is 10,750. Finally, there are our reference materials. Thank you for listening.